So here's a piecewise defined graph or piecewise defined function. We considered the same thing when we did left and right side limits in section 2.4, and now we're going to use it to discuss continuity. And this idea of continuity is not new to you. You've seen it before in college algebra or pre-calculus. You say that functions are continuous if you can draw them without having to lift up your pencil. So as soon as you lift up your pen to draw the function, like we just did at x equals 1, the function is discontinuous. So we would say that is a point, x equals 1, where the function is not continuous. It's also discontinuous at 2. We'd have to pick up our pencil again to draw the graph there. And then we would say that the function is discontinuous at 1 or 2. You might be tempted to say that it's discontinuous at -1 or at 3. Those are the endpoints of the function, so you'd stop and start there. But let's look first at 1 and 2. We can evaluate them or analyze them a little bit in terms of the limits that we've been discussing thus far. What's the limit as x approaches 1 for this function? You can see that as we approach 1, and we talked about from the left and the right side limit idea in section 2.4, the limit as x approaches 1 of this function, f of x, does not exist. However, the limit as x approaches 2 of f of x does exist. We said that that limit is 1. The function approaches 1 as a y value from the left and from the right of 2. However, the value of the function at 2 is 2, not 1. See here, the value of the function is 2. That's where the function exists, which is different than the projected value or the intention of the function, the limit of the function. So that's interesting. We see that the limit doesn't exist, or the limit is different than the value of the function at these points of discontinuity. What about where the function is continuous? Where are some points that we don't have to pick up our pencil to draw, like where x equals 0? At x equals 0, the limit as x approaches 0 of the function exists. That limit is 0. And we also find that the value of the function at 0 is also 0. You could see the same result at x equals half. The limit as x approaches 1/2, so 1/2 is right here, appears to be about 1/2. And in fact, the function, the value of the function at 1/2 is also 1/2. The function goes to that point. So the value equals the limit, and then the function is continuous at 0, at 1/2, at any point between 0 and 1, the function is continuous. So that gives us the following definition in terms of limits. A function is continuous at an interior point C of its domain if the limit as x approaches C of the function f of x equals the value of the function at C. The limit equals the value in words. Like the limit is the same as the value of the function. Returning to our picture, you can see that anywhere where the limit equals the value, the intention matches the reality, then we have a continuous function where we did not have to pick up our pencil. But any place where the limit doesn't exist, or where the limit and the value are not the same, we have a discontinuous point or a point of discontinuity. So that leads us to the continuity test. We can test to see if a function is continuous by seeing if these things are met. The function is continuous at an interior point C of its domain. IFF is a short mathematical way to say if and only if. It's the biconditional. It means that the arrow goes both ways. If one thing is satisfied, then the other thing happens, and if the other thing is satisfied, then the first thing happens. Then the test is 1, find the value of the function f of c exists. 2, find the limit of the function. The limit as x approaches c of the function f of x also exists. And 3, third part of the test, is that the limit as x approaches c of the function f of x equals the value of the function at c. So if they both exist, that's what we prove in part 1. The value of the function exists and the limit exists, and that those two things are equal, then we can say that the function is continuous at the point.